My name is Stephen Victor Kobner from Smart Sonography Institute. Today we are going to be talking about hemodynamics. This hemodynamics course is 4 courses brought together to make one complete course. And this course is an indispensable course for any sonographer or health or ultrasound enthusiast who would want to learn more about the exciting field of Doppler or vascular ultrasound. This course is going to be a precursor of other courses that will be coming, and I am going to be doing modular vascular or Doppler courses like the renal system. I'm also going to do something on the cranial and the intracranial system. I'm going to be doing something on the lower extremity, the upper extremity, the hepatic system, and many other courses that are coming. So this is just a precursor to the courses. So be looking out for all these courses. If you want to extend your tentacles in the ultrasound world, then you need to go deeper. And these courses are going to be very helpful in moving further in your career as a sonographer. All right, so let's dive straight into the hemodynamics course. When we talk about hemodynamics, there are 2 words actually brought together, hemo and dynamics. And the word hemo is actually a combining form, and it is used as a prefix, which means blood. Hemo means blood. And when we talk about dynamics, we are talking about the forces that makes movement possible. So in this respect, we are talking about the forces that makes blood move, all right, or the movement of blood possible. So hemodynamics, when you bring it together, it simply means the movement of blood, the movement of blood. And we are going to be talking about how blood moves in our vascular system as human beings. So by way of definition, I will say that it is a general term, okay, referring to the movement of flow of blood. More specifically, this term refers to the measurement of blood and the general principles governing the flow of blood in the human body. That is just the meaning of hemodynamics. Great. Before we talk about anything else, I want us to know that the cardiac output of the heart is approximately 5 to 6 liters per minute, although that amount dramatically increases with exercise. So every second, every minute, every hour, our heart is pumping. It is pumping and it is distributing blood to all parts of the body. Don't forget that. When your heart stops pumping, you are dead. All right? So this pumping activity of the heart distributes blood to systemic circulation to all parts of the body. And this activity, all right, increases when we exercise. The cardiac output helps to determine blood pressure. So the amount of pressure in your blood at a particular point in time is as a result or is determined by your cardiac output. And so this cardiac output is equal to the stroke volume times the heart rate. So CO, cardiac output, is equal to SV times HR, heart rate. What is this stroke volume? When we talk about stroke volume, the stroke volume is the amount of blood in mils pumped by the heart every beat. So as the heart is pumping, okay, as the heart pumps, the stroke volume is that amount of blood that is pumped by the heart every beat. So at any particular point in time, the volume or the amount of blood pumped by the heart is a stroke volume. Now, when we are talking about blood movement or the principles of flow, we can talk about blood flow, which is represented by the letter Q. Blood flow, Q, is defined as the volume flow per unit time, or the amount of blood that goes through the vessel in a certain time. The unit is liters per minute. And let me just remind you that blood, like all liquids, moves from one point to another because of the difference in energy. So in the body, that energy we are talking about is pressure energy. And the pressure gradient, or a pressure gradient, must be created for blood to move. Without this pressure gradient, blood cannot move. And we'll be talking about that pretty soon. So we need to know also the difference between the volume flow rate or blood flow and velocity. They are not the same, but a lot of times people try to mix it together. So there is a difference between the volume flow rate and velocity. What is velocity? Velocity is simply speed. All right, it is simply speed, how fast this flow is going to move, okay, or how fast the blood is moving through the vessels, and its unit is centimeters per second. I want you to know that. If we are talking about blood flow and velocity, then we also need to know one important factor called resistance. Interesting. When we talk about resistance, it is simply how easy or how difficult a particular vessel allows blood to flow through it. So if we say that a certain vessel is high resistance, it means that it doesn't allow blood to go through it easily. For example, the ICA, or the internal carotid artery, is a low resistance vessel. It is low resistance because it allows a lot of blood to go through it. Now the ICA carries blood to the brain, so it must be low resistance so that blood will be able to go to the brain. If the brain is devoid of blood for some few minutes, the person is going to die. All right, so the blood must be able to reach the brain and in the right quantity. On the other hand, the SFA, or the superficial femoral artery, is a high resistance vessel. But as soon as we begin to do more exercise, the peripheral resistance is going to decrease from high to low. All right. Also, the superior mesenteric artery, SMA, is a high resistance vessel when we are hungry. All right. But when we eat, it is within the abdomen. All right. So when we eat, it is going to change from high resistance to low resistance in order to provide more flow to the intestines for the digestive process. So resistance is very interesting, and this is happening right in our bodies. It is happening right in our bodies. So what it means is that high resistance means low flow, and low resistance means high flow. Don't forget that. High resistance means low flow, and low resistance means high flow. So when we say that a vessel is high resistance, it means that it is not allowing a lot of flow. But when it is low resistance, it means that it is allowing a lot of flow. All right? I hope you are doing good so far. There is a scientist, or there was a scientist by name Huygens Poiseuille, who postulated an equation or a law that flow is equal to P2 minus P1 times pi times R raised to the power 4 all over 8 times L times viscosity. Don't fret. We'll be looking at this equation soon. We'll be talking about it more soon. So he said that blood flow through a vessel, all right, flow is equal to P2 minus P1, and P2 minus P1 is simply change in pressure. All right, change in pressure, times pi, which is a constant, times R, which is the radius of the vessel, all right, raised to the power 4, all divided by 8, which is also a constant, times the length of the vessel, L, times viscosity. I'll be talking shortly about all these variables and what they actually mean. So pressure gradients, let me just chip in this. We need a difference in pressure in order for blood to flow. I just want to repeat myself, all right? It is so important. Note that we need a difference in pressure for blood to flow. And also note this, that blood will always move from a high pressure zone to a low pressure zone. Don't forget that, all right? Don't forget that. Great. So let me show you a picture, an image that I'm going to use to explain what we are talking about, how blood flows. So let me show you this image. Explaining flow. You can see that in the first vessel, okay, in the first vessel, you can see flow direction. It says that arterial flow is 100 millimeters per mercury and venous flow is 100. Now it says that no flow. Now you should understand this, that when arterial flow becomes equal to the venous flow, there is not going to be any flow. There is not going to be flow, because we have said already that pressure must be different, okay, for flow to be possible. So when pressure at the arterial end and pressure at the venous end is the same, there is not going to be flow. All right, pressure gradient must be created for flow to be possible. When you look at the second image, it says that arterial flow is 100 and venous flow is 99. Of course, there is flow. You can see the flow direction. And I told you that flow will always move from arterial end, okay, to the venous end. That is how blood flows to our system. All right, there is flow. And also, when arterial end is 100, okay, and the venous end is 0, there is going to be so much flow. There's going to be so much flow indicated by that arrow. So this is how blood flows and how important it is.